So the first two questions on this exam are limits. For the first one here, the limit as n goes to infinity of the square root of 4n over n plus 2. I don't know how much work someone wants to show here. I would probably bring that limit inside the root and write it as the square root of the limit as n goes to infinity of 4n over n plus 2. I feel like you should be able to say that's equal to the square root of 4. You might use a L'Hopital's rule. You might divide top and bottom by n. I think that's not unreasonable to jump to that point here. But if you really want to, you could say that's the same as the square root of the limit as n goes to infinity. Divide the top and bottom by n. And then I think it's relatively straightforward that 2 over n is going to 0.
Wait,
Mm-hmm.
I don't get how it goes to 4 because you're not 4 and 2, you're not like 2. Like,
So what I'm focusing on here, and so very typically what we focus on when we have a rational kind of expression like this is the highest powers and their coefficients. So the coefficients of 4n and 1n are 4 over 1. Yeah. And even though this exam says you do not need to simplify your final answers, I feel like you should write this is equal to 2. Like leaving the square root of 4 just seems a little, I wouldn't do that. Well,
because it's running.
so let me ask you a different question real quick here. Let's say we had the limit as n goes to infinity of 2n squared plus 5n plus 1 over 6n squared minus 3n plus 7.
You only got 2 on square.
Right, those are the only things that matter because they are kind of dominating each of those numerators and denominators separately. Exactly.
Oh, that's it.
That's it.
Oh,
So that's always going to be the case if the highest power in the top and the bottom are the same. Okay, the second one, this is definitely seeming like an infinity, well, not seeming like, this is an infinity over infinity. And unlike the previous one where we had a different way of doing it, here you do need to use L'Hopital's rule. It's a pretty safe bet that when you have a natural log and you're doing a limit with an infinity over infinity type, you're probably going to have to use L'Hopital's rule. So here we would do the limit as n goes to infinity of 1 over n over the derivative of the square root of n. I would probably think of that as n to the 1/2. So then my derivative is 1/2 n to the minus 1/2. And if I were using L'Hopital's rule, I would either write L'Hopital or I would write, often I say that my limit is equal to, and then I write an L apostrophe H above there to make sure the person knows I'm using L'Hopital's rule. And then we should simplify. This is the limit. You write the limit every time of 1 over n over 1 over 2 n to the 1/2. And then we're going to flip and get 1 over n times 2 n to the 1/2 over 1. This simplifies to, let's see, n to the 1/2 over n to the 1 is just an n to the 1/2 in the bottom. And that n to the 1/2 is going to go to infinity. So the whole fraction is going to go to 0.
is this just 21A stuff, right? So we're just having us do 21A, like there's nothing new than
There's nothing new here. The only difference is the context. And the context is here, this is technically a sequence versus in 21A, we were talking about functions. But they're really, you're totally right. There's no difference. Right, that a factorial in your limit is an animal we didn't really encounter. Not that we couldn't have been asked about that, just it's not what we usually ask about. Let's look at the next one. Also a reminder, just in general, when you take a test, make sure you read the instructions. This one says write down the nth partial sum for the following series and use it to determine what each series converges to. So, two things about this question that I see right off the bat. If they say write down the nth partial sum, it's probably going to be telescoping or geometric. Additionally, if they ask me to find what the series converges to, it's definitely going to be telescoping or geometric. So always good to know that if they ask you what it converges to, you should be like, oh, it's either telescoping or geometric. Those are the only options really. To write down the nth partial sum, I kind of like to just write out the first few terms. So if I was doing this one, I would say, okay, well, this is going to be like my first partial sum is just 1 minus 1/2. My second partial sum is 1 minus 1/2 plus 1/2 minus 1/3. I would simplify this just to kind of help me see the pattern. That's 1 minus 1/3. Next partial sum, I would probably add the first three. So 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. That's going to equal the 1/2s cancel, the 1/3s cancel, 1 minus 1/4. At that point, I'm pretty confident that I know what the pattern is. The fourth partial sum is going to be 1 minus 1/5, all the way down to the nth partial sum is going to be 1 minus 1 over n plus 1. I would recommend if your subscript here is n, using a capital N, just because we like them to be different. But if you use a regular n, that's totally fine. Then to find this, what the series converges to, I would say that the series from n equals 1 to infinity of 1 over n minus 1 over n plus 1 is equal to the limit as n goes to infinity of the nth partial sum. This is probably what your teacher would love to see you write. And then that's going to be 1 minus 0, which is 1. But it is worth knowing or writing that the series converges to the limit of the nth partial sum, if it converges. I'm always less good with geometric ones, to be perfectly honest. I know there's a pattern. I often forget exactly how to write it out. Yeah, so I see that this is geometric because I see that I have a 2 to the n really, or 1 to the n. I might start just writing out terms. That's going to be 3 over 2 squared, right? Because my first term is starting n equals 2. It could be easy to miss that if we weren't paying close attention here. And then 3 over 2 cubed, 3 over 2 to the 4th, and so on and so on and so on. I can see that my ratio here is 1/2. And I know that my first term is 3 over 4. I know what this should converge to. I will fully admit I'm not great at writing the nth partial sum for this type of thing. I don't know why. It's just I feel like I'm always off by a factor of the ratio. Let's try and do it anyway. So, right, if we have to do this, let's see here. So I'm going to get my first partial sum is 3/4. My second partial sum, I really should factor out the 3 and just say it's 3 times 1/4 plus 1/8, which is going to be 3 times 3/8. This is 3 times 1/4. My third partial sum is going to be 3 times. This is where I might start being a little smarter about things. Instead of writing 1/4 plus 1/8 plus 1/16, I might just write 3/8 plus 1/16. Use the previous thing to help me get that thing. And then that's going to be 6/8, 6/16 plus 1/16, which is 7/16. So I'm pretty sure I'm seeing the pattern at this point. Whatever the denominator is, the numerator is half that minus 1. That's what I'm seeing. And I'm going to do that one more time just to be sure. My next term is going to be 7/16 plus the next power of 2, which is 1/32. And that's going to be 14 plus 1 is 15/32. Which still meets the pattern that it's the top is half the bottom minus 1. So if I want to write S5, I like to write the next one just to make sure I know what the pattern is doing. So I'm like, okay, the next one's going to be 3 times, the bottom is going to be 64, the top is going to be half of that minus 1. And then I might write it as 3 times, well, 64 is 2 to the 6th, and 31 is 2 to the 5th minus 1. And then I can say, oh, that means my nth partial sum should be 3 times 2 to the, well, let's see, let's do the bottom first. The bottom is 2 to the n plus 1, and the top is 2 to the n minus 1. Yeah. Oh, sorry. Good call. Thank you. It might have been better to have done it like this. This looks like 3 times 2 to the 5th over 2 to the 6th is 1/2 minus 1 over 2 to the 6th. So I could actually write this as 3 times 1/2 minus 1 over 2 to the n plus 1. And now I'm ready to take the limit. The limit as n goes to infinity of my nth partial sum is the limit as n goes to infinity of 3 times 1/2 minus 1 over 2 to the n plus 1. And we know that this term is going to go to 0 because the denominator is getting infinitely large. That's just going to be 3 times 1/2, which is 3/2. I will point out that this does match what I thought the answer was going to be, right? If we just used our usual formula for the sum of a geometric sum, this definitely is equal to the first term, which is 3/4 over 1 minus the ratio. 3/4 over 1/2 is just 3/2. So it is good to see that that actually is what we thought we would get.
Wait, where did the auto design come from?
Well, there's two ways to see it. I see that I have a 2 to the n in the denominator, so that's really a 1/2 to the n. So my r with half. But I can also just look at each next term, right? This term times 1/2 gives me the next term. This term times 1/2 gives me the next term. And I can see that, oh, every time I'm just multiplying by 1/2 to get to the next thing. Cool. I know I said I'm just gonna start the problem, but yeah, good job. So let's talk about this next one here. 4n over, so the sum from n equals 1 to infinity of 4n over e to the 2n. We're supposed to use, I should read the instructions. Use a convergence test to determine whether the following series converge or diverge. And in the back of our minds, we should think about, can I apply the nth term test? It wouldn't surprise me if at least one of these diverged by the nth term. Here, I don't think you need to write it out, but if you think about taking the limit as n goes to infinity of 4n over e to the 2n, we should be able to convince ourselves that that limit is 0, because the bottom is definitely way bigger than the top. So nth term test doesn't apply or help here, but it's something you should always think about checking if you're doing a convergence or divergence of a series. So nth term test fails. Cool. What test should we try now? We've got lots of tests at our disposal. Which is the one James would pick? I would for sure pick the ratio. Ratios, if I can pick the ratio test, I'm gonna pick the ratio test. It is my favorite test to use, mostly because I don't have to come up with something to compare it to. Now, the other reasons I would use the ratio test here is because I have something raised to the nth power or an n factorial. Those are the two kind of reasons I would choose the ratio test. And here it works. So ratio test, I will point out for the ratio test, technically there is an absolute value around your an plus 1 over an. That's going to be the limit, n goes to infinity of 4 times n plus 1 over e to the 2 times n plus 1. And instead of dividing by an, I almost always like to just multiply by the reciprocal of an. Just a little bit less writing to do. I don't think that's a step anyone's going to fault you for taking. And then we usually group all the like things together. So I'm going to rewrite this as the limit as n goes to infinity of 4n plus 4. I guess I wasn't planning on multiplying it out, but I did. 4n times e to the 2n over e to the 2n plus 2. And I suppose I would do one more step of simplifying here. Limit as n goes to infinity. I've got 4n plus 4, 4n times e to the 2n over e to the 2n plus 2 just ends up being 1 over e squared. And that's e to the 2n over e to the 2n times e squared. All right. As n goes to infinity, what happens to 4n plus 4 over 4n? Right. So we get 1 times 1 over e squared. Now, here's the thing. Once you get to the end of the limit, you have to be able to write the conclusion. That value is importantly what? Or what is it not, I guess, is the question. A terrible question. Right, it's smaller than 1. Thank you, Patrick. Smaller than 1, which means the series converges by the ratio test. Looking at this next one, it does not look like a ratio test to me. I do not see any of the hallmarks of the ratio test. In fact, I'm getting ahead of myself. I should probably try the nth term test. My bet, in fact, I'm pretty confident that the nth term test is going to show that this actually diverges. So I really can't stress enough. when you're looking at series, if it's not immediately obvious the limit of the sequence is 0, you should definitely actually write out the nth term test. Here, also, I feel like if you look back at this first problem, this limit, or the second problem, this limit being 0 means the reciprocal of that limit is probably going to be infinitely large. And this one here, that I just covered up, is really very similar to that, just it's got an n squared, which actually doesn't really change anything at all. So here's what I would take a look at. I say, oh, limit n goes to infinity of the square root of n over the natural log of n squared. Before I use L'Hopital's rule, because I'm going to use L'Hopital's rule, I'm going to write this as n to the 1/2, and I'm going to bring down that 2. So it's 2 times natural log of n. It's not saving you that much work, but it is saving you some work. Then we apply L'Hopital's rule, and oh, look, we get the limit as n goes to infinity of 1/2 n to the minus 1/2, 2 times 1 over n. All right, simplifying, 1/2 over 2 is 1/4. I don't really care about the 1/4. What I care about is the fact that n to the negative 1/2 divided by 1 over n is the same as n to the negative 1/2 times n over 1, which is just n to the 1/2. So here we have the limit, n goes to infinity of 1/4 times n to the 1/2. That's getting infinitely large. I don't really care that it's infinity. What I care is that it's not 0. So this diverges. Cool. I really like my guess, my bet. I would be willing to bet a decent amount of money that your test for sure, and probably Casal's test as well, will have a series that diverges by the nth term test. It's something that people often forget about, and teachers like to make sure that you're aware of. Right, as long as the limit of the sequence is not 0, the series diverges. Right, that's why we also call it the test for divergence. Yeah, so I never want to see anyone write the words converges by the nth term test or converges by the test for divergence. If you write that, you think, oh no, I've done something wrong. You can't converge by the test for only divergence. Cool. All right, here's another one that is screaming ratio test. Maybe you could probably even use the root test, but I almost always use the ratio test instead of the root test, unless it's specifically everything is raised to the nth power. So I would use ratio, and I would say limit n goes to infinity of 4 to the n plus 1 over n plus 1 times 3 to the n plus 1 times the reciprocal of that, which is n times 3 to the n, 4 to the n. Group like things together. So you have 4 to the n plus 1 over 4 to the n, 3 to the n over 3 to the n plus 1, and n over n plus 1. I suppose you could do one more step of simplifying. 4 to the n plus 1 over 4 to the n is 4. 3 to the n over 3 to the n plus 1 is 1/3. And n over n plus 1, when we take the limit, that's going to go to 1. So you're going to get 4 times 1/3 times 1, which is 4/3, which is bigger than 1. So we get divergence. So I would say we know to use the ratio test, or we know that the ratio test is a good thing to try if you see something raised to the nth power like that, or a factorial. So if your sum, has like, 2 to the n over n factorial times n squared plus 1, that's an excellent time to use the ratio test. Or if you only have one of those things, also still excellent. Oh yeah, look at this one here. So here I don't see any of the things that would make me want to use the ratio test. What I do see is powers of n over powers of n. The denominator is a little unfortunate, like they could have made it easier, but they didn't, which is fine. But when I see powers of n over powers of n, I am always going to think limit comparison. So when I see powers of n over powers of n, I'm thinking limit comparison. So if I saw something like this, or something like the sum from n equals 1 to infinity of, say, n squared plus 5n over 3n to the 5th plus 6n cubed plus 1, I would definitely use limit comparison there as well. Here, in this one I just made up, I would limit compare this with the sum from n equals 1 to infinity of n squared over n to the 5th. I'm just looking at the highest power of n in the numerator, highest power of n in the denominator. So here, I think this series is going to do what? If I'm comparing it to the sum from n equals 1 to infinity of 1 over n cubed. I must think it converges because I'm comparing it to something that I know converges as a p-series. Same idea here. Now, here we have to be a little extra careful because our highest power of n in the numerator is n to the first. Our highest power of n in the denominator isn't n to the third, it's n to the 3/2. Because there's that square root on that. And this reduces down to 1 over n to the 1/2, which we know is divergent. So we are trying to show divergence because we're limit comparing with something that is divergent. So if we do the limit comparison test, which is the limit as n goes to infinity of the unknown sequence over the known sequence, so I'm going to write 1 over the square root of n. That's where we always start. Let's flip and multiply. This one's going to be a little bit, usually it's relatively easy. It's a little harder when there's like weird square roots in there. It makes it a little bit more work. The limit as n goes to infinity of n times the square root of n over the square root of n cubed plus 4. Here's what I would probably do to make this easier. I'd probably actually bring this n inside the square root. I'm going to write this as the limit. I mean, you could probably use L'Hopital's rule, but it seems kind of gross. I would write this as the limit as n goes to infinity of the square root of n squared times n over the square root of n cubed plus 4. Because now I can combine that into one big square root and say it's the limit as n goes to infinity of the square root of n cubed over n cubed plus 4. And we know the limit of the inside is going to be how much? Where does n cubed over n cubed plus 4? Right. Right. It happens a lot that you have 1 times n to the highest power over 1 times n to the same highest power. That's going to be the square root of 1, which is 1. And be careful here. It's easy to get yourself confused and think, oh, this test is inconclusive. Because if it was the ratio test and the limit was 1, it would be inconclusive. For limit comparison, you just don't want 0 or infinity. Here we specifically don't want 0. Infinity would be fine for trying to show divergence. So since this is not 0, both series do the same thing. Both series converge. Diverge, sorry. Oh my gosh. Very easy to say the wrong thing, actually. So powers of n over powers of n, limit comparison test all day long. I will also point out if you did do the ratio test here, it would be inconclusive. Ratio test does not ever work for powers of n over powers of n. All right, let's look at, I think there's one last page here. Yeah, cool. All right, everybody should know the answer to the question I'm about to ask. What test is this series screaming at me to use? Definitely. Now, here we actually do need to use the absolute values because you have a negative. So here we should do the ratio. And I would definitely, if I'm doing this test, I'm going to write down ratio test. So this person who's doing my work, reading, knows I know what I'm doing.
Could you just do the absolute? I think that's what
Technically, you should. It's just that when all the terms are already positive, we don't need to write it because it's not necessary. But technically, we are.
As long as there's just one term that's negative.
Right, because here basically this is bouncing back and forth between negative and positive. So I'm going to write this as the limit n goes to infinity of my n plus 1 term, so -2 to the n plus 1 over n plus 1 factorial times the reciprocal of the an term, which is n factorial over negative 2 to the n. Okay. So then, as we always do with the ratio test, we group like terms. So we rewrite this as the limit as n goes to infinity of the absolute value of negative 2 to the n plus 1 over negative 2 to the n times n factorial over. I recommend at this stage rewriting n plus 1 factorial as n plus 1 times n factorial. Because then we can see that the n factorials cancel. So you end up with, and also say negative 2 to the n plus 1 over negative 2 to the n is just negative 2. We have the limit n goes to infinity of the absolute value negative 2 over n plus 1. And as n goes to infinity, what happens to negative 2 over n plus 1? 0, which is less than 1. So this series converges. And just because it's worth mentioning, I will point out that when you use the ratio test and you get convergence, also when you use the root testing convergence, it actually converges absolutely, which is nice to know. All right, so those are some things I would remind / encourage all of you to be kind of aware of when you take your first exam. Patrick later today, the rest of you next Friday. Just to be kind of very thoughtful about reading the questions and look for the kind of key things. Make sure you remember the nth term test. It's always good to think about, especially if it's not obvious that the sequence is going to 0. I mean, here, that's not a good example. Sorry. Where'd you go? Sorry, all my papers are. I would say, like, in this previous example here, I didn't really give the nth term test a second thought because I saw that my power on top was 1, my power on the bottom was like n to the 3 halves. I knew that was going to go to 0 if I took the limit of it. Same deal. Ooh, actually, not the same deal here. I could use the nth term test here, but it's kind of hard to use the nth term test here. I would rather just use the ratio test because the ratio test is easy. That's also why I like the ratio test. It's easy to apply if it applies.
How does it did you cross multiply for that part?
So you mean from here to here?
Yeah.
So I rearranged. So basically, if something's in the numerator, it can go anywhere. If something's in the denominator, it can go anywhere. So what I really have is this times n factorial over n plus 1 factorial times negative 2 to the n. And I can write that in any kind of arrangement I want, as long as the things that are in the bottom stay on the bottom and things in the top stay on the top. So I just wrote it as, because this times this is still the same as that times that, and this times this is still the same as that times that. Right, exactly. It's one big fraction, and we're breaking up it into very convenient pieces where the like things are paired with the like things. Yeah, all right. That seems like a very reasonable-ish test for a first exam. I think I would be happy if that were the exam I were getting. And I imagine this is the actual test he gave last quarter, so I would think that your actual test later today probably shouldn't be too divergent from that. Use math word. All right, so that said, let's go ahead and continue talking about the stuff we were talking about last time, which was why am I in the word math? I don't know. I'm trying to write whatever. Co-class. Let's see, where were we last time? We were talking about alternating series and absolute convergence. Yeah. Sorry, I kind of lost my place here. Oh, yeah, way lost my place. 1 second, please. Yeah, we were kind of talking about absolute versus conditional. Yeah, let's go there. Sure. So let's talk about absolute versus conditional convergence. And so I think I was saying this to Masson yesterday. If you think a series might converge absolutely, it's worth checking, especially like if you've got an alternating series or something that's not always positive, it's really good to check for absolute convergence because something is easier. For example, the sum from n equals 1 to infinity of sine of n over n cubed. There really isn't any other way to show this series convergence other than via absolute convergence, because sine is not a nice alternating series. Sine goes positive, positive, positive for a while, negative, negative, right? It doesn't go back and forth, back and forth, back and forth. So here we would test absolute convergence by just taking the sum from n equals 1 to infinity of the absolute value of sine of n over n cubed, which really, I don't need the absolute values around the n cubed. I'm just going to put them around the sine. Now, once you have tested or started to test for absolute convergence, then you usually have to do something else. Like you're not just ending with the test for absolute convergence, with some exceptions. You then sometimes have to be like, well, I'm going to use the comparison test now. So this certainly is less than the sum from n equals 1 to infinity of 1 over n cubed. So this series converges by comparison with that series, which means our original series converges absolutely. Right. So usually, like, yes, exactly. So we say it converges absolutely. And I don't feel like you should ever have to then write so it converges, because it is always implied that if something converges absolutely, that it converges. But yes, converges absolutely, so it converges. On the other hand, sometimes things don't converge absolutely. For example, I'm trying to keep things fine. I'll rearrange it later. The sum from n equals 2 to infinity of negative 1 to the n over n times. Let me fail. I'm trying to make something up that's not going to be terrible. Maybe this. So sometimes I think this converges absolutely, but let's check and see. Yeah, I feel. Oh yeah, I was going to do it the other way. That's fine. So I would still check for absolute convergence. Now, really, what I would probably do here is I wouldn't check for absolute convergence. I would probably use the ratio test, right? Because I see one of the usual hallmarks. So ratio test. If I do the limit, n goes to infinity of absolute value of negative 1 to the n plus 1 over n plus 1 times 4 to the n plus 1 times the reciprocal. Again, rearranging things so that everything on top stays on top, everything on the bottom stays on the bottom, but like things are with like things. We get that we have the negative 1 to the n plus 1 over negative 1 to the n, and n over n plus 1, and a 4 to the n over 4 to the n plus 1. So we're going to get the limit, n goes to infinity of negative 1 over 4 times n over n plus 1. And that limit is going to be 1/4, less than 1. So this thing converges absolutely. The ratio test does give absolute convergence. So let's actually look at something other than that. On the other hand, if I had, say, oh yeah, we can do that. The sum from n equals 1 to infinity of negative 1 to the n plus 1 times n squared plus 5 over n cubed plus 1. if we start trying to check, well, in fact, let's check. So absolute convergence. So if we look at the sum, you can write the absolute values, but if it's alternating, all you really need to know is that you don't need the negative 1 to the n plus 1. So for absolute convergence, if we're looking at the sum of the absolute value of our terms, it's really just the sum of n squared plus 5 over n cubed plus 1. And what are we thinking this series is going to do? Do we think it converges with a thumbs up and it diverges with thumbs down? Or we're not sure, thumbs in the middle. Right, okay, so I'm thinking, well, since it's powers of n, I know I'm going to think it's similar-ish to highest power of n over highest power of n. And now what do we think? Are we thinking it might be convergent or it might be divergent? Well, what's n squared over n? Yeah, right. We're thinking it might be divergent because this is really very similar to 1 over n. So if we test for convergence or absolute convergence, we're not going to get it. We're going to get, if we use the limit comparison test, the limit as n goes to infinity of n squared plus 5 over n cubed plus 1 all over 1 over n is just going to be the limit as n goes to infinity of n cubed plus 5n over n cubed plus 1, which is 1, which means both this series and this series do the same thing. They both diverge. Now, here's where you have to be careful. We don't get to say the series diverges necessarily. All we can say so far is it does not absolutely converge. But the alternating series might converge on its own. So when you're faced with when you're faced with a question that asks about absolute versus conditional convergence, you should always test for absolute convergence first. And then if it doesn't absolutely converge, then you test for alternating series convergence. And if that is a yes, then you get to say that the series conditionally converges. So literally absolute convergence just means that the sum of the absolute value of the sequence converges. So for example, well, in fact, let's finish this example and then we'll talk about another example. So here, if I look at the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n squared plus 5 over n cubed plus 1 is not absolutely convergent. So now we check to see if the alternating series test shows that the alternating series converges. Right. I should say more specifically, if someone just gave you this series and asked, does it converge? You might just start with the alternating series test because you know the absolute convergence doesn't work. But most of the time when this kind of question gets asked, it's usually more asked in the context of either does it converge absolutely, or does it converge conditionally, or does it diverge? So usually you have to check kind of all the things anyway. So if you have to check all the things anyway, you might as well start with checking for absolute convergence, because if it absolutely converges, you're done. The whole thing converges as well. Whereas if it doesn't, right, if you check the alternating series test first, you might get convergence, but then maybe it still also absolutely converges. So you have to still do the work of checking absolute convergence, even if you've done this already. So alternating series test, thing 1, the non-alternating part, n squared plus 5 over n cubed plus 1 is certainly positive. You almost never really need to check that if you think the alternating series test applies. Thing 2, the limit of the sequence is equal to 0, which it certainly is, because the denominator has a higher power of n than the numerator. And the third thing, which is the worst thing to usually check, is that the sequence is decreasing. So the an plus 1 is less than an. Now you can either check this by actually showing it, or by taking the derivative of your sequence and showing that it is negative after some value of n. And that is usually what we recommend doing as long as you don't have a factorial. So I would say, great, my function f of n is n squared plus 5 over n cubed plus 1. F prime of n is bottom times the derivative of the top minus the top times the derivative of the bottom, all over the denominator squared. And I'm always just going to be focused on the numerator because the denominator is always positive. So simplifying the numerator, I'm going to get 2n to the fourth plus 2n minus 3n to the fourth minus 15n squared all over n cubed plus 1 squared. And then 2n to the fourth minus 3n to the fourth is negative 3n to the fourth minus 15n squared plus 2n all over something that's positive. And I think I can convince myself pretty easily that that is definitely going to be negative for any n greater than or equal to 1. So if I start at 1, I get negative 3 minus 15 plus 2. And then if I plug in anything bigger than 1, these terms out here are going to get way more negative faster than that's going to get positive. So I think we're pretty set here. So we've met all three conditions of the alternating series test. That means the series does converge by the alternating series test. So our series from n equals 1 to infinity of negative 1 to the n plus 1, n squared plus 5 over n cubed plus 1 does converge, but does not converge absolutely. And when this is the case, we say that it converges conditionally. So an alternating series that converges but doesn't converge absolutely is conditionally converged. Yeah, conditional convergence is kind of weird. Yeah, I don't think we need to say this. There are things you can say about conditional convergence about how, like, if you add things up in a different way, conditional convergent series, if you rearrange how you add them up, you can make them add up to kind of anything you want, which seems kind of strange, but it's true. Whereas absolutely convergent series, you cannot. They only add up to one thing. Great.
When we test that it's decreasing, we just take the derivative.
Well, that is one way to show it's decreasing. You can take the derivative and show that the derivative is negative. If you recall from 21a, right, when a function is decreasing, its derivative is negative and vice versa. The only problem is you can't do that if there's a factorial. So if we had to show this was decreasing without taking derivative, the way we would do it is we would literally just start with this inequality, an plus 1 less than an, and throw things into this. So we would be trying to show that n plus 1 squared plus 5 over n plus 1 cubed plus 1 is less than n squared plus 5 over n cubed plus 1, which is kind of, oh, sorry, yeah, apologies. And then you typically cross multiply and end up canceling a bunch of stuff and getting eventually that something is bigger than something else that is true. So if I was going to do this one, I'd multiply out n squared, yeah. So I'm going to get n squared plus 2n plus 1 plus 5 is 6 times this up here, n cubed plus 1, less than n squared plus 5 times this, which is, oh boy, is n cubed plus 3n squared plus 3n plus 1 is 2. And then you would multiply it all out. Seems awful. On the left side, you get n to the 5th plus 2n to the 4th plus 6n cubed, oh geez, plus n squared plus 2n plus 6. Hopefully the person writing your problem has given you a less terrible example of this. And then on the left hand, on the other side, oh boy, you're going to get an n to the 5th plus a 3n to the 4th plus 3n cubed plus 5n cubed is 8n cubed plus a 2n squared plus 15n squared is 17n squared plus a, remember that, plus a 15n plus a 5, so 10, sorry. And then you would try to cancel stuff. So like that cancels, and then you start subtracting over. So you have this minus that is n to the 4th, and that minus that is 2n cubed, and that minus that is 16n squared, and that minus that is 13n plus 4. And yeah, that's definitely positive, right? No matter, as long as n is bigger than or equal to 1, that's going to check out. That's always going to be bigger than or equal to 0 because bigger value, right? All these terms are added together. There's nothing hard to see about that. Sometimes you get weirder stuff where it's like some minus signs in there, then you actually have to kind of think a little bit more about it. But usually showing something is decreasing, decreasing like this is straightforward. Just terrible algebra multiplying things out.
So we can do it that way.
You totally can do it that way. Literally, we're just showing that the next term, an plus 1, is smaller than the previous term. That means the terms got smaller. It doesn't matter what n is, for any n that's greater than or equal to 1, the next term will always be smaller than the previous term. The problem is, this is not too terrible if like it's rational function over a rational function. This gets a lot worse to try and check if you have logarithms or exponentials or kind of anything other than just powers of n over powers of n. Right, yes. I definitely recommend showing that f prime of n is less than 0 if that is an option to try and show something's decreasing. Okay, let's see here. Sure. So the place where we should start talking, I know we only have like 4 minutes left, but we should definitely start talking about power series. So power series. So we have already found the sum of some series, right? We know, for example, that 9 plus 3 plus 1 plus a third plus a ninth, 27th, go on. That's a geometric series. I can see that my ratio is 1/3, and that's definitely going to add up to the first term over 1 minus my ratio, which in this case is going to be 9 over 1 minus 1/3, which is going to simplify to, I don't know, 9 times 3 halves, which is 27 halves. So what if instead we wanted to find a series that adds up to 10? So we want our first term plus our next term plus our next term plus our next term plus forever, never equal 10. And the only condition here is that we're making it geometric. We know that to get from there to there, we're going to multiply by our ratio r. Okay. So pick any first term you like. Maybe I should be able to pick a term less than 10. I'm trying to make it easy on myself. I'm gonna pick 5. So I know that if this is a geometric convergent series, then it's going to add up to 5 over 1 minus my ratio. So all I need is that denominator to end up being essentially division by 1/2, because I want this to be 5 times 2, which is really 5 divided by 1/2, which is really 5 divided by 1 minus 1/2. So I want my ratio to be 1/2, I guess. My next term is 5 halves. My next term is 5/4. My next term is 5/8, and so on and so on and so on. I can definitely find a geometric series that adds up to any number I want. So the reason we're talking about this is because instead of adding up to a specific number, we're going to have our geometric series add up to a specific function. So instead of saying this plus this plus this plus this equals this number, what we're really going to say is we can have, say, and I don't want to be coy about it here, 1 plus x squared plus x cubed plus x to the 4th, forever, never. Well, it's a geometric series. My first term is 1. My ratio is x. So it is true that the function f of x equal to 1 over 1 minus x is indeed equal to the geometric series from n equals 0 to infinity of x to the n. With one important caveat. X can't be too big or too small. Just like for a geometric series, we have a radius of convergence, or I should say that the ratio has to be between -1 and 1. That's also true here. The ratio x has to be between -1 and 1. So this is true as long as x is between -1 and 1. And this here is called the interval of convergence. This series converges to this function as long as x is between -1 and 1. But it certainly wouldn't be true if x were, say, 3, right? 1 over 1 minus 3 does not equal 1 plus 3 plus 3 squared plus 3 cubed, and so on and so on and so on. This thing over here diverges to infinity. This is equal to -1/2. So functions converge to their series on the interval of, I should say, series converge to their functions on the interval of convergence. We'll talk more about that on Friday. Today is Wednesday.